All right, hello everyone. This is our live session for February 16th. We are ecstatic to have you here. My name is Matthew, and I do some of the behind the scenes stuff. I'm part of the course staff for our online classes, which we host through Udemy and Coursera, but many of you here are here from other venues. So we appreciate you joining us. I'm going to let Professor Impey say a quick hello, and then we will get started with your questions.
Okay, thanks everyone for being here live or submitting your questions by email. So the floor is open for your questions on astronomy.
Excellent. The first question is from one of our emails. John Benson has a question about doing infrared astronomy with small telescopes. So can you talk about the possibilities of doing amateur observing from small scopes in the infrared spectrum, for example, seeing and recording brown dwarfs?
Right, that's a good question because amateur astronomy is now has the availability of really sophisticated equipment in terms of CCDs for optical imaging. Infrared observations for amateur astronomy are more challenging. It's not that the detectors and the instruments are not available at all. They are available, and some of them are not extremely expensive because thermal imaging or infrared imaging is, of course, used in industry and in various parts of the commercial world. It's not just an astronomical application. But for astronomy, you actually need a quite special purpose infrared instrument because it has to image from the telescope onto the focal plane of a detector, and to work in the infrared, the detector has to be cryogenically cooled, and at the very least, that requires liquid nitrogen. So it's a quite more sophisticated piece of instrument. It's more finicky. It's more difficult to handle. It involves a dewar or a cryostat. It involves those cold temperatures. It involves a supply of liquid nitrogen. Liquid nitrogen is also an industrial product. It's about as cheap as milk, so it's not that exotic or special. It's just liquefied air, if you like. But you do need liquid nitrogen to keep the thermal background down enough to make an infrared image. And the detectors, pixel by pixel, are more expensive than a CCD optical detector, and you're likely to get less real estate of pixels. So arrays, I think commercially available arrays are more like 32 by 32 or 64 by 64, as opposed to the kilopixel by kilopixel, which is a megapixel cameras that are easy to obtain. So I would not say it's off limits for amateur astronomy, but it's a more challenging setup. And also, if you want to work at the very limit of observation, you need a pretty dark site, ideally high altitude and dry, because water vapor interferes with infrared radiation. And if you want to be at the limit of your sensitivity, you actually need to baffle and coat your telescope in sort of thermal, reflective, or absorptive coatings to reduce the emissivity of the telescope, which could interfere with your detection. So all around, it's a more challenging proposition. There are handbooks that you can find online of how to do infrared astronomy and some tips on where to find these detectors. I don't know any off the top of my head. So I would encourage you to try it. It's a very important niche of astronomy for amateurs to pursue.
Excellent. Yeah, that's really interesting. I didn't even know that that was possible unless you were high on a mountaintop or in outer space. So that would be really fun. The next question from one of our live participants is from Dimitris, who would like to know if there are efficient models to predict dust storms on Mars and when Perseverance, which is going to land tomorrow, might face its first dust storm.
That's a good question. I've seen a couple of articles that relate to Martian weather and include the idea of localized dust storms. The answer is no. Especially at the local level, at the level of small-scale weather. I mean, as we all know, there are beautiful animations taken by some of the rovers over time of dust devils on Mars. So there are miniaturized dust storms, small-scale dust storms, that over the history of Martian rovers have both coated their solar panels with dust, reducing their available power. And then in one very lucky occasion with one of the Spirit and Opportunity rovers, I forget which one, a dust storm or dust devil came along and fortuitously cleaned off the solar panel and increased its sensitivity by 50%. So, you can win and you can lose with dust storms on Mars in terms of the hardware there. At the small scale, they're simply not predictable, just like very small scale weather is not predictable on the Earth. The only type of dust storm that's predictable at any degree on Mars are the sort of continent scale or sort of hundreds of kilometers or maybe 1,000-kilometer scale dust storms. And they're predictable because they're powered by solar irradiance. Of course, solar energy is the main driving force, and of course by the Mars rotation and the wind, the typical winds aloft, depending on latitude on Mars. So I think people have the ability to predict the huge scale dust storms, which are episodic, and every few years there's a pretty significant dust storm on the scale of a fraction of the planet, but not the small scale stuff.
The next question is from Ru Mu, who would like to know if you can discuss the isotopic, either isotopic or maybe mean isotropic, but can you discuss the isotopic signature of water from the solar system and how the water cycle may have gotten started on Earth?
Right. So there's a way of diagnosing the origin of water by looking at isotope of water. Obviously, an isotope is a variant of the H2O water molecule that involves an isotope of one of the atoms. And for example, if it's deuterated water, it involves deuterium as one of the atoms along with oxygen. And this has a different history. So it's a way of looking at the history of water because water on Earth has a particular ratio of normal water to deuterated water. And if you're looking for the source of the water, the original source of that water in extraterrestrial bodies, you want to measure that same ratio because obviously the Earth must have got its water in a way that generally preserves that ratio over time because it's not possible for that ratio to typically change. And that has been used to show that deposition of water by comets and in water-rich bodies from the outer solar system, the so-called late Veneer model, is not actually fully supported by these isotopic ratio measurements. And so that's opened the door to other models for the formation of the water on the Earth. And maybe the more used to be not as popular but now more popular model is that the water was already there and that it was there at the formation in the deep mantle, and it was eventually sort of extruded out through the deep mantle by water temperature, by pressure and temperature, to eventually rise to the surface to become the oceans. So yes, the isotopic ratio or ratio of water in its normal and its heavy isotope form is a very important diagnostic of where that water came from in the first place.
Excellent, thank you. I'm glad you recognized that because I wasn't sure where they were going. That was wonderful. Lawrence would like to know, in an expanding universe, I assume dark matter becomes more diffuse like regular matter. Does dark energy diffuse in an expanding universe? And if not, would that mean that some conservation laws are being violated?
Yeah, it's an important question. And yes, dark matter does reduce in density with the expansion of the universe because we think dark matter is simply a particle. It's probably a subatomic particle. And there was a finite amount of it created in the Big Bang, and it's been essentially diluting or diffusing as space expands over time. And so, yeah, the density of dark matter is going down with the cosmic expansion, along with the normal matter at the same rate. However, dark energy appears to be a different type of entity. The reason we think it's associated with the vacuum of space, some form of vacuum energy, if you like, is that it appears that the strength of dark energy, its sort of mass energy equivalent strength, does not seem to vary with time or location in space. And that means as space-time expands and essentially as more space is created, the amount of dark energy stays constant. And that's imputed to be because it's a product of the vacuum. And so it's, as you create more space, more vacuum, you create more dark energy. And so its strength is not going down over cosmic time. It's essentially remaining constant. And so the influence of dark energy in the cosmic expansion is increasing over time. We see, for instance, at the moment that dark energy exerts about 2/3 of the influence on the expanding universe, causing it to accelerate, and dark matter exerts a 1/3 influence, which would make it decelerate. Since dark matter is going to continue to decline in importance, and dark energy already dominates by a factor of 2, it's almost inescapable that the future of the universe is accelerating expansion.
Excellent. Thank you very much. The next question is from one of our live participants. Chandran would like to know what you think of Milgram's Mond theory as an alternate explanation for dark matter.
So Mordecai Milgram is a well-known astrophysicist, and he's been the champion of an alternative form of gravity theory that mitigates or obviates the need for dark matter. We still don't know what dark matter is. As physicists are still searching for it, probably a fundamental particle. But everyone is pretty much leaving the door open for the fact that the theory of gravity may be wrong. If you modify the force law of gravity by a very small percentage, actually, you can get rid of the need for dark matter on large scales in galaxies. And Milgram's modified Newtonian gravity, that's the acronym MOND, does this. And it has some significant successes. It can explain the flat rotation curves of galaxies without the need for dark matter. It can explain the way galaxies move in clusters. It can explain a lot of the large-scale structure in the universe without the need for dark matter, essentially by tweaking the gravity law. There is a cost to this, however, and the cost is that you remove a fundamental conservation law in physics. It's related to Gauss's theorem. By having gravity alter from an inverse square law. That's actually a big change, and it's a big sacrifice to the symmetry, elegance, and conservation aspect of gravity theory. So the jury is out. I would say the consensus of opinion is that while Mond does explain most observations, it doesn't explain all of them. And it definitely is not as elegant or beautiful a theory. It's been well worked out by the people who support it. So there's many papers have been written on it, dozens, perhaps hundreds at this point. But the jury is out on whether it can be refuted or whether we really need to go to such a radical idea of jettisoning Newtonian gravity on large scales.
The next question is from Mohan, who apparently saw a news item that the Earth is rotating faster now. So can you talk about whether the rotation of the Earth has changed and how it changes over time?
Yeah, the rotation of the Earth is it's changing very slightly, and of course it changes very slightly even during the year. Once you can measure the rotation of the Earth and the length of a day with atomic clocks, you will find minute variations in the rotation period of the Earth even during a cycle around the Sun. More interesting perhaps are the long timescale variations. The biggest influence on the rotation speed of the Earth, or the length of the day if you like, is the influence of the Moon. And because the Moon is tidally locked to the Earth, and that's why the Moon presents one face towards the Earth, and that gravitational interaction has a couple of effects. Energy and angular momentum have to be conserved, and so what we find is that the Moon is gradually moving further away from the Earth, very small amount, I think it's about 4 centimeters a year. It's actually a measured amount because of the reflectors the Apollo astronauts left on the Moon. And that coupling of energy and angular momentum and the increasing distance of the Moon means that the Earth's speed over very long timescales is actually slowing down. And so the day is actually getting slightly longer. There's inference that billions of years ago the day was maybe as little as 14 hours or 12 hours even. So over long time scale, due to that effect, the day is actually lengthening.
Excellent, thank you. The next question is from one of our live participants as well, who would like to know, Keith would like to know if you can please explain the concept of local standard of rest and how it is used in astronomy.
The local standard of rest is you need a reference frame when you do astronomy, when you look at celestial objects. You need a reference a location for time and position, of course. The Earth is moving through space, it's spinning, and it's orbiting the sun. And the local standard of rest is just a reference that allows you to synchronize a clock, or synchronize any clock you have at different parts of the world based on the spinning rate of the Earth. And that reference is typically located with reference to the stars or sidereal time. So local standard of rest is defined with reference to a grid or framework of stars, because those stars are far enough away and are moving with absolute speeds that are high, but speeds through space relative to their distance from us that are quite modest. And so they form a sort of fixed reference for what we would call the local standard of rest.
The next question is from Kokila Harini, who would like to know, the question is, what do you mean by a wormhole? And so I think what they're asking is, what is a wormhole, and can you talk about sort of what we know about them, or what we think we know about them, or whether they really exist?
Yeah, a wormhole is a potential outcome of general relativity. That is to say, it's allowed by our best gravity theory, formulated by Einstein a century ago. And it's essentially a portal in space-time. It's a place that connects two disparate locations in space-time by essentially pinching together the space-time, so you can travel instantly from one place to another without traversing a large distance in 3 dimensions. It would require space-time at that situation to be highly curved and complex, because you can't have a wormhole without having highly curved space-time, curved in on itself essentially. So while it's allowed by theory, we have seen no evidence that it happens in the real universe. Now, we have black holes that are bounded by event horizons, places from which no information can escape, but nobody has ever had any suggestion that the black holes that we know of in the universe connect to distant regions of the universe, and therefore are wormholes. They could be, theoretically, of course, and since we can't travel into a black hole and then get out again, we don't formally know. But it's all the evidence suggests that the space-time curvature at the point of a single black hole and its event horizon are not mapping to a different region of the universe, which is what would be required for a wormhole. So the notion of wormholes in science fiction as ways to travel almost instantaneously across large chunks of the universe, it's very fanciful, and there's no evidence to support it.
Excellent, thank you very much. The next question is from Dennis, who would like to know if you have any thoughts on what we can expect from the new Mars rover, Perseverance.
Yeah, the new Mars rover is very exciting. It's essentially a twin of the Curiosity rover that's been on Mars for some years now. So most of the hardware of the vehicle itself and its drivetrain and its solar panels and so on are almost unchanged. They upgraded, of course, and improved where they could, but part of this cost saving was by not redesigning it from the ground up. What is new is, however, the instruments, because it has 7 instruments, and the instruments it has are somewhat different. There's some overlap, but there are some are quite different from the ones on Curiosity. In particular, miniaturization of sophisticated scientific instruments has got better over time, and so they're able to pack more capability into the small packages that are required for a Mars rover. The most exciting ones are the instruments that can do very sensitive spectroscopy of vaporized rocks or reflectance spectroscopy of rock and crystal and mineral surfaces, and deduce what the composition of those minerals and rocks are at a very sensitive level. So they can look at high resolution spectroscopically and tease out all the components of these minerals and rocks, which is to say not just the normal rocky material, silicates and carbonates, but also potentially biological material, biogenic material, which is to say amino acids or molecules that are implicated with biology. Nobody expects active biology in a surface rock on Mars because of the sterilizing effect of the UV radiation in its thin atmosphere and cosmic rays. But these instruments potentially could see the traces of prior life. It's not really looking for fossils. Again, we don't really expect large fossilized life forms, although the cameras are, of course, good enough that they could see microfossils if they existed. And also the rover can dig some centimeters down, so it doesn't have to just use surface rocks. It can dig for interesting rocks at some distance from the surface. But it can barely go below the level that is sterilized by the UV radiation, so it's not clear that it can get to a true subsurface layer where life might have been incubated or isolated from the harsh environment of the surface. Either way, this rover is going to have several years of very exciting exploration. It's landing in the Jezero crater, which is known to be a sedimentary formation where there was almost certainly liquid water hundreds of millions or a billion or so years ago. And so with sedimentary rocks and layers and formations, it is indeed possible that if ancient life existed on Mars, it might find some traces of it.
The next question is from Alexa. Why do the outer gas giant planets rotate faster than the inner terrestrial planets?
It's a little bit a question of angular momentum. So there's more net angular momentum, or absolute value of angular momentum, mv squared over r, or mv over r squared. Either of those is larger for an outer planet than an inner planet because they have a lot of mass. And they're formed from material fairly far out, so the lever arm of distance from the center of mass is large. So forming in a part of the protostellar disk where there's a lot of angular momentum, the planets themselves have a lot of angular momentum. And that means essentially that they're spinning quite fast. Since the outer planets have rocky cores that we can't directly observe, we're reduced to measuring the speed of rotation of the outer gaseous atmospheres made of hydrogen and helium. It's likely there's differential rotation, not just between the poles and the equators, but also between the outer layers and the inner layers. So we have to just speculate what the interior speed, say, of the rotation of the solid core might be.
Excellent. The next question is, again, from one of our live viewers. Surge would like to know, how does the sun's magnetic field sustain in such extreme temperatures? So I'm not sure whether they mean how does it sustain temperatures or how does the magnetic field exist in such extreme temperatures, but perhaps you can talk about the connections between the magnetic field of the sun and the temperature.
Right. The sun got its magnetic field from primordial magnetic fields. You can't create magnetic fields from nothing, from absolutely nothing. And so the interstellar cloud, or the protosolar nebula, was threaded with weak magnetic fields, and as the sun gravitationally collapsed and formed a stable object, the field lines that were entrained were squeezed, and the magnetic field strength increased, and so you ended up with a collapsed object with a significant magnetic field, and it has a polar magnetic field just like a bar magnet. The reason the magnetic field can be retained is that the sun is a plasma. So the sun is a medium where the protons, mostly hydrogen with some helium, but where basically you have protons and helium nuclei and a large number of electrons moving at high speeds, relativistic speeds, because it's a plasma. And within that kind of a medium of charged particles in free motion, magnetic field lines can sustain because the motion of the charged particles is not going to destroy the magnetic field. In fact, the charged particles respond to the magnetic field and they move around the field lines in spiral patterns. That leads to synchrotron radiation or cyclotron radiation. So having formed a magnetic field and it being sort of tethered by the squeezed plasma of the dense core, it is unlikely to go anywhere until the sun winds up the magnetic field due to differential rotation, and eventually it's destroyed and then has to reform, and that's the solar cycle.
The next question is from one of our live participants. Students Library would like to know if parallel universes exist.
We don't know, and it's going to be hard to answer that question. Even the notion of parallel universes, which sounds like a science fiction concept, it comes from one aspect of the Big Bang, which is to say the inflationary theory. The inflationary model posits that the very early universe underwent a very dramatic expansion, exponential expansion, in a first tiny fraction of a second after the Big Bang. This inflationary idea is motivated by the fact that the universe is smooth and essentially flat. and inflation provides an explanation for why space has that property. But it also includes the idea that the universe began as a quantum entity, because inflation occurred at the time when the universe was the same scale as quantum type processes. And so the speculation is that the universe was expanding, and its expansion was the result of a quantum fluctuation. And if you have one quantum fluctuation in this pre-Big Bang state, maybe you can have others. And so you have the essence of the idea of parallel universes from the quantum genesis of the universe. That theory, that idea, does not tell you anything about the nature of these parallel universes, what their properties might be, although they could easily be quite different from the properties of our universe, and more particularly how you would detect them. Since they're distinct space-times, in principle, it's not obvious that you ever could detect them. But some theorists speculate that there may be gravitational waves that indirectly couple parallel space-times that emerge out of inflation, and that might be a signature that you could look for. But at the moment, there's no active experiment to test the multiverse theory.
The next question is from David Gold, who would like to know if there's any kind of research that's being done in the field of astronomy that might be able to allow us to mitigate the severity of hurricanes on Earth.
Not really. So astronomy and climate science, have some connection, of course, because affects, the sun most obviously, but other phenomena in space do have an effect on the weather. But severe weather, in terms of hurricanes or the extreme weather that we see happening more and more, is imputed as a result of climate change, or global climate change that's warming the planet due to our own carbon dioxide and greenhouse emissions. And that sort of means the answer and the mechanism and the cause are within our hands. They're not really related to astronomy. And astronomy really doesn't have any particular tools to bring to bear on this. This is climate science. It requires sophisticated modeling of climate. It requires supercomputers to understand all the inputs and the levers that apply to a climate model. Astronomy uses some of those same tools, similar models, similar supercomputers, but doesn't have any actual direct impact on climate science research.
Excellent. The next question is from Otaku Ops. Generally, to look for life, we need to follow the water. So doesn't it make sense to look for life on one of the moons of the gas giants instead of going all in on Mars?
That's a good question. And the phrase "follow the water," of course, it came from NASA. So NASA's planning, starting a decade ago, was that in their exploration of the solar system, they would follow the water. The premise here is, which needs to be inspected and seen if it's a good assumption, is that life needs water. So if you find a place that's too dry, you won't expect to see life. That's a fair bet, because all forms of life we know have substantial amounts of water. I mean, humans are about 2/3 water, jellyfish are 98% water, even the driest beetle you could imagine is 40% water. So water is indeed an ingredient of all forms of life on Earth, and life probably started in the oceans or hydrothermal vents or warm ponds. So it's a fair premise. And in those terms, yes, Mars is not the obvious place you would go, because Mars has no surface water. It very likely has subsurface aquifers, but these are not available for us to inspect, because they're likely to be tens, maybe hundreds of meters under the surface, and we can't diagnose them except indirectly by radar. So we do have radar indications that there's a lot of subsurface ice and probably water on Mars. So there is water, and in the sense of following the water, Mars is not a terrible place. It just means you have to go underground to know what's going on. Or look for the traces of life on the surface, where we think surface water existed for a long period of time when the Martian atmosphere was thicker and denser, and so Mars had a higher temperature, enough to allow liquid water. But generally, there are other places where the water is not necessarily more accessible, but more omnipresent. Europa is the obvious one, the watery moon of Jupiter. But that's also hidden by a deep ice pack. We don't know how thick. It may be as thin as 100 meters or a few hundred meters, or as thick as 5 to 10 kilometers. So that's not really much more accessible than Mars. And all the other places where there's water in the solar system are also likely to be inaccessible, because they're in the outer solar system and would be under a cap of rock and ice. So in that sense, it's not obvious that there are any better places to look for life in the solar system than Mars, which is much closer.
The next question is from Hytrans. You have previously discussed finding gravitational waves from collapsing black holes. What other events will provide us with gravitational waves, and have we found any?
So the main signatures, the first signatures and the most so far for gravitational waves are emerging, not collapsing black holes. You would get gravity waves from the formation of a black hole, as an aside, but the main measurements so far are emerging black holes, binary black holes, as they coalesce. And there have been 15 or 16 examples of that. The other things that will produce gravity waves are, of course, mergers of other compact stellar corpses, which is to say neutron stars. And we've now observed neutron star mergers that generate gravitational waves, and also electromagnetic radiation, which is exciting because you can identify the source of the gravitational waves quite accurately. You also might expect to see mergers between neutron stars and black holes. None has been seen by LIGO yet, but we would anticipate to see those as well. The other things that could generate gravitational waves that we might anticipate are a supernova explosion, which leads to the formation of a compact object, including black holes, especially if it's asymmetric. The larger the asymmetry, the larger the gravity waves produced. But gravity waves are produced by any change in a mass configuration, so supernova will do that. And so those are the main signatures for gravitational waves that we know we can detect, and probably out to large distances. The wild card and the uncertainty is whether we can detect gravitational waves from the early universe, from the Big Bang itself, when in principle they were produced in abundance and then have been traveling out through space since then. The nature of that signature is not clear, and it's not clear also whether LIGO has either the sensitivity or the signal filtering capabilities to detect gravity waves from the Big Bang. But that's a sort of frontier piece of research right now.
The next question is from Hernan Reyes, who is in France, and I believe is on with us right now, but also sent an email. You've discussed the forthcoming Europa Clipper mission that will hopefully be launched within a couple of years, but would it be possible to convince motivated donors to go all in on like a truly exceptional mission to Europa? And what are the challenges behind building something like that, or planning it, or finding funding for something that would scoop up and analyze matter on the surface and send a robot submarine through the ice?
Yes, the Europa Clipper is an important step forward in our understanding of Europa. It's still a decade off, of course. It's a long time to plan, launch, and get to that system, 1 billion miles away. But NASA's had more ambitious plans in the past, and they may one day be funded, and perhaps by the private sector. So there's been a design on the drawing board for actually a couple of decades for a Europa lander, which would include a nuclear plant, which would try and land, of course, on the thinnest area of the ice crust. So that would need some serious reconnaissance by orbiters before you got to the lander stage. And having found the thinnest part of the ice crust, hopefully only maybe a few hundred meters deep, that's plausible, you actually use a detachable part of the lander and its nuclear energy released just by its power source, just by nuclear thermal energy essentially, to slowly melt the way through the ice, and then when you get to the bottom of the ice layer, release a hydrobot to look for life. So that design's been on the books for, I think, almost 20 years now. So it's, the technical challenges are understood, and they're definitely soluble. That mission would be even easier to do now because of miniaturization and just better equipment that NASA has access to. And it's hard to know what the price tag would be. NASA's not planning something that ambitious initially, which means to do that with NASA would take 20 or 30 years. That design could essentially be taken off the shelf and modified and executed by a private corporation or a donor. And I'm going to guess that the cost of that would be $2 billion. It's hard to tell what the costs are, but you can't do anything in the outer solar system for less than $1 billion, and something that sophisticated probably substantially more. But that's, of course, within the means of any number of billionaires. in the world, let alone the large corporations like Amazon, owned by Jeff Bezos, who has space aspirations. So it may well be the way it happens.
The next question is from Rue Mew again, who would like to know where do or can amateur astronomers publish their findings?
Well, I mean, if amateur astronomers are doing, legitimate research and analyzing data and making a contribution to the subject, they can publish in exactly the same journals that professional astronomers do, and that happens. It doesn't happen, very, very often, but it does happen every year. So I would say at the first instance, amateur astronomers with publishable data that's competitive in some subfield of astronomy should just look to the same journals professional astronomers use. There's no stigma, there's no bar to publication based on not being at an academic institution. And indeed, there's some academics who retire or end up leaving universities who don't have affiliations with an academic institution, and they publish too. So the first part of the answer is just the same journals that astronomers publish in: the Astronomical Journal, the Astrophysical Journal, publications of the Astronomical Society of the Pacific, monthly notices of the Royal Astronomical Society, and Astronomy and Astrophysics, which is a European journal. Those are the sort of top 5, if you like. Much harder, just for any professional astronomer, let alone amateur astronomer, is to get published in Nature or Science magazine. Those are just hard magazines to get research published into. There's also publications from the American Association of Variable Star Observers, AAVSO, and they have their own journal, and amateur astronomers quite often make observations of stellar variations and variability. So that's another example, and so there's quite a lot of choices.
The next question is kind of related to a previous one. The gravitational waves question. What will happen if a neutron star and a pulsar collide?
Well, a neutron star and a pulsar. Pulsar is a neutron star. Pulsar is just the subset of neutron stars where there's a blemish on the surface that creates a place where low energy radiation is emitted from a hotspot. That low energy radiation is radio waves. And those radio waves emit cyclotron radiation due to the intense magnetic field. And when the rapidly spinning object sweeps this hotspot across the beam of a radio telescope, you see a pulse of radio emission, and it repeats with the period of the pulsar. That's what a pulsar is. That's how they're detected. So the pulsars are just the subset of neutron stars that are visible to radio telescopes. So when a pulsar and a neutron star collide, it's essentially the same as two neutron stars colliding. I think the extra effect of the hotspot that leads to the pulsing radio emission would not make a substantial difference into the outcome of two neutron stars colliding. The gravitational wave signature would probably be largely similar. We don't think we've seen this yet. Of course we would know, because hopefully the pulsar, we'd be able to identify its location on the sky, and then if we saw gravitational waves from that part of the sky, we could infer that the pulsar that we can see in radio waves had combined with something we couldn't see, another neutron star, to produce the gravitational wave signature. It would be very exciting if it were seen.
The next question is from Kokila Harini, who would like to know, can a 13-year-old girl become an astronaut?
I think teenagers can apply. There's a youth astronaut. NASA has a program that's a sort of development program for future astronauts. I don't think you can formally apply for the astronaut program. I don't think any astronaut has been, I know there's been no astronaut younger than 21. I'm not sure what the youngest is. That's an interesting question. But no, at 13 you can't go up into space under anyone's aegis. Any other country would have the same rules. But I know you can apply to the youth feeder program for astronaut, which just gives you information on the astronaut program, shows the path by which you would eventually apply, lets you learn about the program, about what is required of astronauts, what typical training they have in terms, because they all have degrees in technical fields, and so how you would position yourself to have the best chances of being an astronaut. Now, of course, the private sector is now playing a big role in space with SpaceX and blue origins. And so civilians are going to go up into space. And the private sector, will have different rules than NASA. I don't think they'll be launching 13-year-olds anytime soon, or maybe by then you'll be 16 or 17. But they will not be bound by the same government regulations exactly as NASA is. So it may well be that your quickest and earliest shot to get into space, if not formally been asked to be an official astronaut, is through one of the private sector players who will be doing this routinely in a couple of years.
The next question is from one of our live participants. Simon Wells would like to know if you can talk about some of the recommendations that are in or will be in the next Decadal Survey, and maybe you can talk a little bit about what the Decadal Survey is.
Right. The Decadal Survey is an important thing that astronomers do every 10 years, as you can imagine from the title, which is to set their funding priorities. Astronomy is not the only field and wasn't the first field to do this. Geologists, planetary scientists do this, geologists do this, physicists do this. I'm not sure about life sciences. But it's a very important process because in a limited funding climate from the federal government, it's often the case that projects just compete with each other, and it becomes a diminishing resources idea or zero-sum game. And then it just becomes who speaks the loudest, who's the most influential, who has the best network or connections. It could be nepotism in the worst case. So as an antidote to that, some fields, including astronomy, have gathered their august members every decade to form commissions and panels that are deciding the priorities of the field. Overall, they're taking input from the community. Typically on the Astronomy Decadal Survey, there's a main group, the top level group that's about 20 people, and then there are panels below that that are about a dozen in number, with each also with 15 or so people. So hundreds of astronomers are giving input to this report, and they're soliciting input through public forums and websites and mailings from the entire community. So it's a very bottom-up process where the ideas of the best things to do in the next decade percolate up to this top-level committee, who write a report. It turns into a book. National Academy of Sciences publishes these. I was involved in the two ago Decadal Survey on the education panel. It's a very rigorous process. It's doing a difficult thing, though. It's trying to prioritize very different projects, from, say, gravity waves to infrared astronomy, so space astronomy, to ground-based astronomy, to human resource issues like what funding should there be for fellowships and so on. And that's pretty hard to prioritize that thing. Typically it's revolving around big facilities because those are the expensive things. So it's pretty much making a list of the facilities at the level of maybe $500 million and larger and giving a priority. The problem of doing that is that as things slow down and funding doesn't come in, sometimes projects that were high priority in a previous decadal survey don't happen in time. James Webb Space Telescope was the first, essentially the top priority of a previous decadal survey, and it's still not gone up yet. So the problem is that with the slowing down of the launch of these things and the limited budgets, sometimes your priorities for the current decadal survey collide with previous things that have not yet been funded or completed. For the next decadal survey, it's likely that completion of at least 2 30-meter scale telescopes for ground-based astronomy will be a top priority. And in space, it will be the W-FIRST mission. It will be a successor, also a successor to the JWST, because JWST is going to go up, so in 10 years it'll be reaching the end of its life, so you need to understand what the successor will be. And the successor, not a direct successor, will be a large-scale survey telescope that can do Hubble depth observations but over much larger regions of sky. There are also likely to be recommendations about a next level of gravitational wave detectors, including those in space, like the LISA mission that NASA's imagining. But the priorities are not yet clear, so it's going to take another year or so before we know.
Anthony Moore sent an email and would like to know, what are your thoughts about the possibility that we live in a holographic universe and that our 3 dimensions are just an elusive consequence of this 2-dimensional membrane described by string theory?
Well, it's a provocative idea. The holographic universe, it has different manifestations. It's become a sort of catchphrase for various ideas in theoretical physics and cosmology. But certainly one version of it posits that there from string theory, that there are higher hidden dimensions. And so the 3 dimensions of space and 1 of time that are familiar to us, that we occupy and that our current theories describe, are just manifestations of a higher dimensional space-time, which could have 2 or 3 or more extra dimensions. And the question becomes, how can you test an idea like this when all you see are 3 dimensions of space and 1 of time? And the answer is you have to look for interplay between the hidden dimensions and the dimensions that we live in. There are some physics experiments that are trying to do this, because there are subtle effects that percolate up from quantum scale and very high energy scale to laptop physics. And so there are actually physics experiments, one at Los Alamos and one at Livermore that I know of, that are trying to look for graininess in the space-time continuum that indicates higher dimensions at play. Those experiments are not fully operational yet, and it's not even clear if they're sensitive enough to succeed. So it's a very hard idea to test the holographic universe idea or the idea of extra dimensions. It's at the cutting edge, I would say the bleeding edge of physics.
The next question from Phantom Prince, who's on with us live. Usually we say that a perpetual machine is impossible. However, an atom, say a hydrogen atom, seems to live forever with an electron whirling around its nucleus. Will an atom ever stop having this happen?
That's an interesting question. So it's rephrasing it, are atoms perpetual motion machines and therefore violating some law of physics? So it's a good question. And I think the easiest way to see that there's no necessary violation of physics law from the fact that atoms, like hydrogen atoms, have been around for 13 billion years, since soon after the Big Bang, and will persist into the far future. The easiest way to see that is to realize that the kinetic model of an atom, the Bohr atom, where you have a small dense nucleus and a whirling set of electrons around it, is not really how physicists understand atoms anymore. And so if you get away from this kinematic or dynamic model of particles in motion within an atom, then you can sort of finesse this whole idea of energy conservation or violating laws of physics. In fact, quantum theory just posits that an electron is just a probability energy distribution around a nucleus, and the nucleus has its own energy probability distribution. And in quantum theory, there's a time variable part of the Schrodinger equation, and you can play forward the states of atoms, and there's no indication of a time constant attached to this, or energy loss or decay. And so the atoms and their properties in terms of quantum mechanics are indeed eternal, because there's no indication that these quantum states are actually going to decay or evaporate or change on any long time scale.
I just want to address, there are a couple of questions that have come up. One about the radio signal from Proxima Centauri, and another question about recent discussion about Oumuamua being extraterrestrial in origin. We've talked about those recently on live streams, so we're not going to get to those today, but if you want to check out our last 2 live streams, we have discussed those extensively there. So I don't want you to think that we're ignoring you, but just so you know, we've covered those recently, so we won't be doing it again today. But the next question that we're going to move on to is sort of related to orbits. BB Mark would like to know, why is it that the sun's gravitational force is strong enough to hold huge, very far away planets in place, yet the Earth does not fall into the sun?
Okay, it's a good question. Just to follow up what Matthew said, on some of these topical issues, like Oumuamua is a good example, where there's been a very high-profile book by Avi Loeb about it being an alien artifact. We can keep answering questions about that when there's new information, but essentially the other examples given, the last few sessions have encompassed all the information there is. But if astronomers get new information, they will definitely can address these again. The nature of the sun holding Earth into its orbit, exerting over a distance of 100 million miles and holding a very massive object like the Earth into the orbit without it falling in, does seem mysterious until you remember that the gravitational force is a cumulative attractive force where it gains by the mass of the object, and it's an infinite range force. That's the key. So gravity is cumulative. It's always attractive, as opposed to electrical forces, which can attract or repel depending on the positive or negative charge. Gravity simply accumulates. So when you have a large mass like the sun and a much smaller mass like the Earth, the total gravity of these objects is not insignificant. Now, in Newton's simple formulation for two objects, the force the sun exerts on the Earth is exactly the same as the force the Earth exerts on the sun. And when they're in orbit or in motion, the gravitational potential energy is equal to the kinetic energy of the objects in motion, the Earth in this case orbiting the sun. The reason it can hold a large object, the sun can hold such a large object as the Earth at such a large distance, is because the force only declines as the square of the distance. So that means that's quite rapid. So if you double the distance, the force is 1/4, but it doesn't ever go to zero. The force is an infinite range force, and it's that infinite range of an inverse square force that gives gravity its strong reach. So the combination of that rather gentle fall off in the force law and the cumulative effect of an entirely attractive force with large amounts of mass composing an object is why the Earth always stays in its orbit, but doesn't fall into the sun because it's in an energy balance situation.
Eugene Elevato, who's on with us live, would like to know if you can comment on the largest radio telescope that was built in China and what it might be used for, and if it has given any major contributions to astronomy at this point.
Yeah, the large telescope in China is acronym is the FAST. I can't remember what FAST stands for. FAST. It's larger. It's 500 meters in diameter. The F is for 500, I'm sure. And it's a similar idea to Arecibo, which of course was recently lost to astronomy. So Chinese telescope is not only the largest, but doesn't have any close rival anymore, unless Arecibo is rebuilt and maybe rebuilt bigger. This radio facility has been fully operational for about 1.5 years, maybe 2 years. And actually very recently they opened it, they declared it mature enough that they started to take proposals and accept collaborations with astronomers outside China. So it's now a truly international facility, which is very exciting because radio astronomers have been looking forward to something that large. It's the same idea as Arecibo. It's built in a natural depression in limestone type formations that form a natural bowl, and so it does not steer on the sky. It's a transit telescope where the motion at the focus of a feed allows you to scan a strip of the sky that passes overhead. You can't look at the whole sky. Obviously it has very high sensitivity. It tends to work at long radio wavelengths of centimeters or several centimeters rather than millimeter or centimeter waves. That's what the VLA would do. And it's making, I won't say it's made any major discovery yet, but it's really only the first year or so of its operation. So we can anticipate some nice discoveries from it in the future. FAST stands for the 500-meter aperture spherical telescope. Right. And then another question that came up earlier was about the youngest astronaut, and that was Russian astronaut German Titov, who was 25 years old, and he flew on Vostok 2. The next question will be the second to the last. Do you think that we humans are made from the chemicals and dust that comets leave behind? That's an interesting question. So there's been discussion for years and some controversy over what materials have been deposited on the Earth by comets. There was a maverick astronomer, Fred Hoyle, very famous astronomer, and Wickramasinghe, his collaborator, who hypothesized that comets actually contained full genetic information, that is to say viruses and maybe even bacteria, and that they had seeded the Earth with these. So in fact life came from beyond the Earth. This idea is called panspermia. This has fallen out of favor and was never really strongly supported by data. So it's not likely that cometary material falling to the Earth has actually had any substantial role in the development of life, except that comets do have amino acids, they have bases and lipids and for simple molecules that are the ingredients of life. These molecules also exist on the Earth and can form naturally. So it's not clear that comets have accelerated the existence of life. With one exception, potassium is an important trace element in biology. It's obviously implicated in ATP, adenosine triphosphate, which is the energy storing molecule, which uses phosphorus. Phosphorus and potassium are important in biology, and some comets have an extraterrestrial material have large amounts of these important ingredients, and so that's led some people to say that the energy storing molecules of life benefited from the deposition of cometary material. The other important ingredient that comets have provided to the Earth, of course, is water, frozen water. And it's a question that's still unresolved, what fraction of the Earth's water came from comets. We know it's not the majority, but it's probably a significant portion. So yes, comets have deposited material on the Earth over cosmic time, and that material may be important for the development of biology and for the fact that the Earth is a fairly watery planet. But otherwise, most of the material on comets is very similar to terrestrial material.
Excellent. So we have come to nearing the end of our live session. We have one more question. Before we address that question, I want to mention a couple of upcoming events. Tomorrow, we have a live stream on our Twitch channel that will be all about the Mars mission and about Perseverance and the landing. So come check that out. It will be some of our team members. Professor Impey won't be there for that, but some other astronomy students and staff from our team will be there. And then for those of you who are subscribers to our Twitch channel, Professor Impey will be doing a special subscriber focused question and answer session coming up in the near future, and I will announce the date and time for that when we know. I believe it's been scheduled for early in March, so for anyone can join and listen, but subscribers specifically will be able to ask questions, and we'll talk about some beyond astronomy things about your career and experiences in astronomy. So for the last question, we have a chance for you to sort of, think broadly, Chris. If you had an unlimited budget to build the telescope of your dreams, what kind of telescope would that be, and which space objects would you hope to detect or survey?
Well, my training is an optical astronomer. And infrared, so I'd probably stay in that wavelength regime. I think with a real vast resource, I would want to vault ahead of the current generation of large telescopes that we're planning, including the one in Arizona, the Giant Magellan Telescope. So the current huge telescopes of the near future are 20 to 30 meter telescopes. The ability to do much larger than that, say 100 meters, which would really get you incredible light gathering power, is quite limited on Earth. It's just very hard to build the mechanical structure. So for my dream project, I would have a telescope on the moon. Now that's been conceived of for decades actually, but we've never really had the infrastructure on the moon to build an observatory on the moon. But it's likely there will be a moon base in the foreseeable future, and with that infrastructure, then building a telescope there becomes much more feasible. The advantages to the moon to astronomy are enormous. If you robotically operated on the dark side of the moon, you're free from Earthshine, and you will have the darkest sky you can possibly imagine because the moon has no atmosphere. So it's almost perfect observing, the kind you get with the Hubble Space Telescope. But even the Hubble telescope has backgrounds because it's in fairly low Earth orbit. So I would say a giant telescope of order 100 meters on the moon would be my dream project. And it could actually be executed probably in about 30 or 40 years. I think it's even plausible. And the cost of it would not be exorbitant. It wouldn't be vastly more expensive than any of the 20 or 30 meter telescopes we're currently building. Okay, well, thanks for that out-of-the-box question to finish with, and for the good variety as always. We have our next one scheduled already for next week. I think it's Wednesday at 1 Mountain Time. That's our time. And so thanks for Matthew for facilitating, and we'll be with you next week.
Excellent. And I did look up that that bonus stream will be Tuesday, March 2nd at 11 o'clock Mountain Time. So that'll be starting right now, 2 weeks from today. So thank you all for joining us, and we will see you hopefully tomorrow and then next week for our live streams. Take care, everyone.